Today we'll discuss ISI's 2017 UGB paper, and this paper again has some fabulous questions. We'll start with the first question, and it says, let the sequence AN be defined by tan n theta, where tan theta, which actually is A1 and it is 2. We need to show that for all n, AN is a rational number which can be written with an odd denominator. So what we can do is, we can write tan n theta minus n minus 1 theta, so which actually is tan theta, and we can write this as tan A minus tan B upon 1 plus tan A tan B. So we'll write this as tan n theta minus tan n minus 1 theta upon 1 plus tan n theta and tan n minus 1 theta. Then the question, it says the value of tan theta is 2. So we'll cross multiply, then we can write tan n theta minus tan n minus 1 theta, and it will be equal to 2 plus 2 tan n theta into tan n minus 1 theta. Now tan n theta is an and tan n minus 1 theta is an minus 1. So we can write an minus 1, and it will be equal to 2 and then 2 an into an minus 1. So we'll take an together, then we can write an as 2 plus an minus 1 upon 1 minus 2 an minus 1. Now it is already given that A1 is 2. Now we'll put n as 2, then we can write A2 as 2 plus A1 upon 1 minus 2A1, which is minus 4 by 3. So here in the denominator we have an odd number. So A1 we have 1 and A2 we have 3. So we'll prove this result using principle of mathematical induction. So first step is, we'll prove that P1 is true. What is P1? P1 is A1, which is simply 2 upon 1. So this denominator, it is an odd number. So that means P1 is true. Now we'll assume that let Pk be true. So it simply means that we can write Ak as sum P upon Q, where Q is an odd number. Then we need to prove that Pk plus 1 is true. So we'll write Pk plus 1. So Pk plus 1 will be simply Ak plus 1, and there will be 2 plus Ak upon 1 minus 2 Ak. So it will be 2 plus P upon Q, 1 minus 2 P upon Q. So we'll get this as 2Q plus P upon Q minus 2P. Now this Q minus 2P is clearly an odd number. Since 2P is even and Q is odd, so odd minus even is an odd number. So we can say that for all n, an will be a rational number which can be written with an odd denominator. Now question number 2 is, consider a circle of radius 6 as given in the diagram below. Let B, C, D and E be the points on the circle such that B, D and CE, when extended, intersect at this point A. If AD and AE have lengths 5 and 4 respectively, so this AD is 5 and AE is 4, and DBC is a right angle, then show that length of BC is 12 plus 9 root 15 by 5. So what we'll do is, we'll join this CD. Now we know that in a circle, AD into AB must be equal to AE into AC. Now AD is 5, so we'll get 5AB and LB equal to 4AC. Now in this triangle ABC, we can write AB square plus BC square, and it should be equal to AC square. Now we can write AB as 4 by 5 AC, so it will be 16 AC square upon 25 plus BC square, and it is equal to AC square. So from here we'll write BC square is 9 AC square upon 25, that is BC is 3 by 5 times AC, and AC is 5 by 4 times AB, so it will be 3 by 4 times AB. Now in this triangle DBC, the CD is diameter, therefore value of CD is 12. So in this triangle we can write BC square plus BD square. Now BD is AB minus 5 whole square, and this value, it must be equal to 144. Now we can put the value of AB. AB is 4 by 3 BC. So we can write BC square 4 by 3 BC minus 5 whole square, and it is equal to 144. Now this is nothing but a quadratic equation in BC. We can write this quadratic equation as 25 BC square minus 120 BC plus 225, and it is equal to 1296, which is 25 BC square minus 120 BC minus 1071 equals to 0. So we'll solve this equation. We'll get BC as 12 plus minus 9 root 15 upon 5. Now 9 root 15, this value is greater than 12. Length of the side cannot be negative, so we'll choose plus sign, and that's your answer to question number 2. Now in question number 3 it says, suppose a function is defined by fx equals 1 if x is equal to 1, and then e to the power x to the power 10 minus 1 plus x minus 1 square sine 1 upon x minus 1 if x is unequal to 1. We need to find the value of f dash 1. Now first we'll check its continuity at x equal to 1. So value at 1 is 1. If we'll put left hand limit or right hand limit, it will be e to the power 0, which is 1, and then it is 0 into sine infinite, which again is 0. So this function is continuous at x equal to 1. Now we'll find its derivative at 1. Now f dash 1 will be equal to its right hand derivative, which is f dash 1 positive. So we'll write it as limit h tends to 0 f 1 plus h minus f1 upon h. Now this value will be limit h tends to 0. Now what is f1 plus h? f1 plus h will be e to the power 1 plus h to the power 10 minus 1 plus h square sine 1 upon h, then minus f1. f1 is 1 upon h. Now we'll split this limit in two parts. We'll write limit h tends to 0 e to the power 1 plus h to the power 10 minus 1 upon h, and plus limit h tends to 0 h sine 1 upon h. Now the second limit, it is of the form 0 into sine infinite, and sine infinite is oscillating value from minus 1 to 1. So 0 into anything finite is 0. So value of this second limit is 0. Now this first limit is 0 upon 0 form. So we'll use L'Hopital's rule. So we'll differentiate. We'll write limit h tends to 0. Now this is e to the power 1 plus h to the power 10 minus 1 into 10 1 plus h to the power 9 upon 1. Now we'll put h as 0. Then we'll get e to the power 0, which is 1. So this value is equal to 10. And in this problem, I should also work out its left hand derivative. So if I'll find f dash 1 negative, I'll take f1 minus h upon minus h. This part will again be 0. Here I'll have minus h and minus h. So minus and minus, again it will cancel. So again I'll end up getting this value 10. So I won't solve this left hand derivative part. So value of f dash 1 is 10. Now we need to solve this limit, which is limit u tends to infinite 100u minus u, this summation k varies from 1 to 100 f 1 plus k upon u. So we can write this as limit u tends to infinite, and then it will be 100 minus this summation k varies from 1 to 100 f 1 plus k upon u upon 1 upon u. Now we'll put u as infinite, it will be f1 and f1 is 1. So 1 plus 1 plus 1, 100 times, so it will be 0, and then 1 upon infinite is also 0. So it is 0 upon 0 form. And if it is 0 upon 0 form, again we can use L'Hopital's rule. Alright, limit u tends to infinite. Now this is 0 minus, and then this summation k varies from 1 to infinite f dash 1 plus k upon u into now derivative of k upon u. So it will be minus k upon u square divided by minus 1 upon u square. Now 1 upon u square and 1 upon u square will cancel. F dash 1, value of f dash 1 is 10. So we'll get this limit as limit u tends to infinite minus 10, and then this summation k varies from 1 to 100 into k. So it will simply be minus 10 and then n plus 1 upon 2. So this value will be minus 50500. Now in question number 4, we are given a square whose vertices are 1, 1, 1 minus 1, minus 1, 1 and minus 1, minus 1. So we'll draw this square. So this is 1 comma 1, this is 1 comma minus 1, minus 1 minus 1, and this is minus 1 comma 1. Now we need to find this region R, which is the set of points inside S which are closer to center than to any of the 4 sides. So we have any point, say P, x comma y. So distance from center, which is PC, it must be less than distance from any of the side. Now since this problem is symmetric in all the 4 quadrants, what we'll do is we'll solve this problem in the first quadrant, and then we'll multiply this area in the first quadrant with 4 to get area in the region R. Now in the first quadrant, the condition is this CP, which is under root of x square plus y square, it should be less than distance from both the sides, which are 1 minus x, and also we'll get x square plus y square, and it is less than 1 minus y. Now we'll square it, we'll get x square plus y square, it is less than 1 plus x square minus 2x. So here x square will cancel. We'll get this result as y square is less than minus 2x plus 1, which is a parabolic inequality. And here if we'll solve it, we'll get x square plus y square, and it is less than 1 plus y square minus 2y. Again here y square will cancel. We'll get this condition as x square is less than minus 2y plus 1. So this is parabola opening left, and this is parabola opening right. So in the first quadrant, we need to find the region which is common to both the inequalities. So basically, if we'll draw these two parabolas, then this parabola in the blue, it is x square equals minus 2y plus 1, and this parabola in the red, it is y square equals minus 2x plus 1. Now in the first quadrant, we need to find area of this region which is common to both the parabolas. Now we know that these two equations, they are inverse functions of each other. So we'll interchange x and y then we'll get either of the two equations. So that means this area, it is symmetric about y equals x line. So first we'll find this point of intersection. So we'll put y as x, then we can write x square equals minus 2x plus 1. So it'll be x square plus 2x plus 1 equals 2. So x plus 1 whole square is 2. So value of x is minus 1 plus root 2. So this point, it will be root 2 minus 1 and root 2 minus 1. Now since these two areas, they are symmetric about this y is equal to x line, so what we'll do is we'll actually find this area. So area of this shaded region, it is given by this integral from 0 to root 2 minus 1, then y of upper curve. Now y of upper curve in this case is 1 minus x square upon 2. So y, it will be 1 minus x square upon 2. So we write 1 minus x square upon 2 and then minus y of lower curve, which is simply this straight line, which is minus x dx. So we can actually write this as 1 by 2 from 0 to root 2 minus 1 and then 1 minus x square plus 2x. Now we'll add 1 and subtract 1 also. Then we can write this as 1 by 2, 0 to root 2 minus 1 and then 2 minus x plus 1 whole square into dx. Now we'll integrate it. So we'll integrate, we'll write 1 upon 2 and then here it will be 2x and then minus x plus 1 whole cube upon 3. So this area, it will be 1 upon 2 into 2 and then what's the value of x? X is root 2 minus 1 and then minus 1 by 6. If we'll put upper limit, so it will be root 2 cube minus lower limit is 1. So this area will be, now we have 8 such regions. So area of this region will be given by, and that is the answer to this question. Now question number 5 is, let g from n to n be a function such that gn is product of digits of n. Now we need to prove that gn is less than equal to n for all n belongs to n, and then for all n we need to find the values of n such that n square minus 12n plus 36 is equal to gn. Now suppose we have any number n, say 12, then this function gn is defined such that we are going to multiply these digits 1 and 2, so it will be 2. Suppose we have any number which is 1, 2, 3, then gn will simply be 1 into 2 into 3 and that is 6. So for any given number we can always find gn, which is simply product of all the digits. Now first part is we need to prove that gn is less than or equal to n. Now since we have to write this n as a product of all the digits, we can write this n as let n equals a0 plus a1 into 10, a2 into 10 square, ak into 10 to the power k, where each of a0, a1 and ak minus 1, they belong to this set from 0 to 9, and this ak, it cannot be 0, so it belongs to this set from 1 to 9. Now we know that maximum value of a0, a1 and any ak minus 1 is 9. So we'll take their maximum value, then we can simply write a0 into a1 into a2 into ak minus 1, and it should be less than or equal to 9 to the power k. Now we'll multiply it with ak, then we can write a0 a1 a2 ak minus 1 into ak, and it should be less than or equal to 9 to the power k into. Now 9 to the power k into ak is always less than or equal to 10 to the power k into ak. Now 10 to the power k into ak plus all these other terms is equal to n. So we can simply say 10 to the power k into ak is less than or equal to n. Now this product on the left hand side, a0, a1, a2, ak, it is nothing but it is product of digits of n. So it is nothing but gn. So from here we can say gn is less than or equal to n. So that's our first part. For all n belongs to n, gn is always less than or equal to n. Now we'll solve this second part. The second part is we need to find n such that n square minus 12n plus 36 is equal to gn. Now we have already established that this gn is less than equal to n. So it is less than or equal to n. So we'll solve this inequality. We'll write n square minus 13n plus 36. It should be less than or equal to 0. Now we can factorize it. N minus 4, n minus 9. So we'll write n minus 4 into n minus 9 is less than equal to 0. That is, value of n should lie between 4 and 9. So now from this interval 4 and 9, we need to find all those values of n such that n square minus 12n plus 36 is equal to gn. Now in this interval, we know that it is a single digit number. And if it is a single digit number, then the value of gn is simply n. So if we'll take gn as n, then we'll get equality sign here. So that means we'll get only two values of n, and they are n equals 4 and n equals 9. And that is the answer to this question. Now question number 6 is, let P1, P2 and P3 be primes with P2 is unequal to P3 such that 4 plus P1, P2 and 4 plus P1, P3 are perfect squares. Find all possible values of P1, P2 and P3. We can write 4 plus P1, P2 as some n square, and we can write 4 plus P1, P3 as some m square. Then we can simply write P1, P2 as n square minus 4, which is n plus 2 into n minus 2, and we can write P1, P3 as m plus 2 into m minus 2. Now we'll write possibilities for P1, P2 and P3. Now P1 cannot take both the values as n plus 2, m plus 2 or n minus 2 or m minus 2, because in that case n will be equal to m, then P2 and P3 they'll be equal. So we'll consider this case when P1 takes the value n plus 2, then P2 takes the value n minus 2. Now P1 also takes the value m minus 2, and P3 it takes the value m plus 2. Now from this first result we can write m equals n plus 4. So P1 is n plus 2, P2 is n minus 2, and P3 is m plus 2, which is n plus 6. Now what we'll also do is, since this is the smallest one, we'll say this value is k, then this one is k plus 4, k, and k plus 8. So we must get P1 as k plus 4, P2 as k, and P3 as k plus 8. Now k cannot be 1. If we'll take this as 2, then these two numbers, they are not prime. So we'll start with k equals 3. So we'll take k as 3. We'll get this value as 7. It'll be 3 and this is 11. So the three numbers which are prime, they are 7, 3 and 11. Now what about numbers greater than 3? Now any number greater than 3, it will be of the form 3q plus r, where r is 0, 1 or 2. So we'll take this k as 3q plus r, then k plus 4 will be 3q plus r plus 4. So we can write this as 3q plus 1 plus r plus 1, and the same way we can write this as 3q plus 2 plus r plus 2. Now these three numbers, r plus 1, r and r plus 2, they are three consecutive numbers. So if we have three consecutive numbers, then at least one of them is divisible by 3. And when any one of them is divisible by 3, then this number can no longer be a prime number. So that means for k greater than 3, there will be no such P1, P2 and P3. So the only values possible for P1, P2 and P3 are 7, 3 and 11. Now question number 7, it says that there be a set A which is 1, 2, 3 up to n, that is set of first n natural numbers. For a permutation P which is equal to P1, P2 and Pn of the elements of A, let P1 denotes the first element of P. Find the number of all such permutations P so that for all ij belongs to A, if I is less than j is less than P1, then j appears before I in P, and if I is less than j but greater than P1, then I appears before j in P. So we have set of n numbers 1, 2, 3, 4, 5 and then some number k up to n. And again we have 1, 2, 3, 4, 5, k up to some value n. Now let us say, suppose P1 is k. So that means this one, it is mapped to this number k. Now the condition says if I is less than j and it is less than k, so that means for all the numbers which are less than k, which in this case is 1, 2, 3, 4, 5 up to k minus 1, j should appear before I in P. That means all these numbers, their order must be descending. That is 5 must come before 4, 4 must come before 3, 3 must come before 2. So that's how we have to arrange these k minus 1 numbers. Now when k is less than I is less than j, that is for all the numbers which are greater than k, which actually are n minus k numbers, I appears before j in P. So that means these numbers, they have to be arranged in ascending order. So now the problem is, if P1 is equal to k, then in how many ways we can arrange these n minus 1 numbers so that these k minus 1 numbers, they are in descending order, and these n minus k numbers, they are in ascending order. Here the simple fundamental is, suppose we have n1 plus n2 objects, then number of arrangements of n1 plus n2 such that order of n1 should not change and order of n2 should not change is given by factorial n1 plus n2 upon factorial n1 and factorial n2. So we have to arrange these n minus 1 numbers in such a way that order of k minus 1 numbers should not change. They should appear in descending order, and order of n minus k numbers, it should not change. So it can be done in factorial n minus 1 upon factorial k minus 1 factorial n minus k, which is nothing but which is n minus 1 c k minus 1. So if P1 is k, then total number of such permutations is n minus 1 c k minus 1. Now we need to find number of all such permutations. So number of all such permutations is given by this summation n minus 1 c k minus 1 when the value of k varies from 1 to n. So it will be this series which is n minus 1 c0, n minus 1 c1, n minus 1 cn minus 1, which is 2 to the power of n minus 1. So the number of such permutations will be 2 to the power n minus 1. Now question number 8 is, let qx be a polynomial which is x to the power k plus a1 x to the power k plus 1 plus an x to the power k plus n. Now we need to show that this function which is qx upon x to the power k is strictly positive when the value of mod x lies between 0 and 1 plus summation I varies from 1 to n mod ai. Now we look at this qx upon x to the power k, we can write this as 1 plus a1x a2x square plus an x to the power n, and let us say this is some function gx. So we need to prove that when x lies between 0 and 1 upon 1 plus summation I varies from 1 to n mod ai, and this value in the denominator is greater than 1. So this expression 1 upon 1 plus this summation will be less than 1. So that means when the modulus value of x lies between 0 and 1, this function gx, it should be greater than 0. Now how do we prove that? What we'll do is we'll take up these expressions. So we'll say mod of a1x plus a2x square plus an x to the power n, and it is always less than or equal to mod a1 mod x mod a2 mod x square plus mod an mod x to the power n. Now we know that when a number lies between 0 and 1, then mod x to the power n is less than mod of x to the power n minus 1, and it is less than mod x. So that means this complete expression will always be less than or equal to mod of a1 plus mod of a2 plus mod of an into mod x. Now we know that if mod x is less than a, then x lies between minus a and plus a. And since we have to find minimum value of this expression, we can write a1x plus a2x square plus an x to the power n, and this value, it should be greater than or equal to this minus a. So it is minus and then this summation ai into mod x. Now what we'll do is we'll add 1 also. Now we'll add 1, then we can write 1 plus a1x a2x square plus an x to the power n, and it is greater than 1 minus summation mod ai into x. Now this expression on the left hand side, it is nothing but gx, which is qx upon x to the power k. So we can write gx, which actually is qx upon x to the power k, and it is greater than or equal to 1 minus then this summation mod ai into mod x. And the question, it says we need to prove that if mod x lies between 0 and 1 upon 1 plus summation mod ai, then this gx is greater than 0. So minimum value of this gx will occur when the value of this expression is maximum, and the value of this expression is maximum when the value of x is maximum. So the maximum value of mod x is 1 upon 1 plus summation mod ai. So we can write this gx, it is greater than or equal to 1 minus summation mod ai upon 1 plus summation mod ai. So which is 1 upon 1 plus summation mod ai, and which is clearly greater than 0. So that means when the value of mod x lies between 0 and 1 upon 1 plus summation mod ai, then the value of this gx is always greater than 0, and that's your first part. Now we'll come to its second part, and its second part says px is b0 plus b1x b2x square plus br into x to the power r. If m be the smallest number such that bm is unequal to 0. So that means all other coefficients before m, they'll be 0. Then we can write this polynomial px as bm x to the power m bm plus 1 x to the power m plus 1 plus br x to the power r. Now we'll take x to the power m common, then we can write px as x to the power m, and here it will be bm plus 1x plus br x to the power r minus m. Then the first part we have already proved that if x lies between 0 and 1, then qx upon x to the power k is strictly positive. So it simply means px upon x to the power m, which is bm plus 1x plus br x to the power r minus m. This expression is positive in the neighborhood of x equals to 0. So what we can do is we can write this px as x to the power m, and then this expression bm plus 1x and br x to the power r plus m, this expression, it will be positive in the neighborhood of 0. That means sign of px will only depend on sign of x to the power m. So if we'll take p 0 minus h, it'll be minus h to the power m into positive value, and then p 0 plus h will be h to the power m and then positive value. So this 0 plus h will always be positive. Now we'll take this first case when m is an even number. So if m is an even number, then in that case p 0 minus h, it will be minus h to some even power which is positive, so it will be plus into plus, so it will be plus, and then p 0 plus h, it will also be positive. So there is no sign change at x equals to 0. So this graph, it does not cross x-axis at origin if the value of m is even. If the value of m is odd, in that case p 0 minus h, it will be minus 1 to the power m, so it will be minus into plus is minus, and then p 0 plus h, it will be plus into plus, it will be simply plus. So sign of this expression changes when the value of m is odd. So this function, it is going to cut the x-axis at the origin, that is, it is going to change sign at x equal to 0 if and only if m is an odd integer.